Good morning, everyone. Thank you for joining our sessions today, especially I saw some people already arrived really early. We appreciate that. So my name is Mingshi Liu. I'm the machine learning engineer from Amazon Web Services. I'm here today with my colleague, Praveen.
Hello, everyone. First of all, thanks for joining us today. My name is Praveen Mohan Prasad. I work with AWS as an analytics and AI specialist. Thanks for joining again.
Cool. Today we are going to talk about unlocking insights from multimodal PDF using OpenSearch and vision language models. As a brief introduction, what is OpenSearch? OpenSearch is community-driven, open-source search, analytics, and vector database that will allow you to do high-performance AI search and visualizations solutions. Here's a roadmap that you can scan and see what are the upcoming open source features that's coming up. If you're interested, please comment and give it a thumbs up so that it gets more attraction for the future roadmap. The next coming month, September, marks 1 year anniversary of OpenSearch joining Linux Foundation. It's a really exciting milestone for us so that we can maintain the open and innovated and supported by a wide range of contributors contributing to OpenSearch. So now it comes our main quest today. Now you already know what OpenSearch does. We're going to talk about how can we unlock the PDF documents in search. So here comes the concept RAG. Today is OpenSearch. Today is AI Dev Console. I'm pretty sure you're not new about the RAG concept. It stands for Retrieval Augmented Generations. In a very high-level architecture in OpenSearch, here's how it works in OpenSearch. When users are asking a question, we usually will generate vectors for these query tokens, and it fetch the documents in OpenSearch cluster. And these documents will serve as a context, and it will augment it by the prompts. You can understand it as the LLM will follow those prompts as instructions, and it will answer the questions. Those LLMs will serve as a brain that will think about intelligently, answer the question based on those contexts. And this is a really common architecture in a lot of applications using OpenSearch in their RAG so that they can build chatbots, agents, and Q&A applications. In ML Commons repos in OpenSearch, we make those machine learning integrations very easily. Because using a connector, you can try to think about, you can connect to your remote services like OpenAI or your Bedrock so that you can connect any model that you want to choose. And you can bind those models in ingest pipelines so that every time you ingest your documents, you can run model inferences or other data processing. Once your document is ingested, those processing or machine learning prediction can be saved along in your documents. And the story doesn't end here. So once your documents are ingested with those machine learning capabilities, when you're in search, you can also invoke search pipelines so that you can invoke the models and you can rewrite your models, you can rewrite your queries or enrich your documents using those machine learning capabilities. Here we have the barcode that you can scan. We have the supported connectors to many of the model services that I just listed out. Or you can also host your local models, such as you can download those large language models to your local cluster. For example, you can use Llama. Those are for free, and then you can host it in OpenSearch and use in your ingest, or either you can use it on your search. So with this machine learning integration in OpenSearch, it makes it pretty simple to achieve RAG use case. And these are the documents. But the real challenge nowadays are in your RAG applications are the documents plainly in text? No. The challenge nowadays are documents are multimodal. Thinking of if you have a PDF, then some of them are text, some of them are graph, and some of them are tables. Those rich medias are pretty hard to understand by a large language model. So thinking of in search, how do you search for example, some of the textual information from the graph or the tables so that when you ask the questions, you can fetch relevant context and feed it to LLM and you can let LLM to understand those graphs further. So this is the challenge that we're going to solve today. We have two solutions. So the part one, I'm going to talk more about this, is how we can ground multimodal into text representation. Then we can generate them into text embedding. Then later you can use vector search and use it on RAG applications. And the second approach is a more lately trending approach is to use vision language model. This model can understand not only text, but also text and graph and tables jointly. So you can use it to handle multimodalities. Later, my colleague Praveen will talk more about that approach too. So before we dive into how to build up this approach, I want to show you how multimodal RAG demo looks like. We actually have a demo website. This is built up on the top of OpenSearch. So in this multimodal RAG, we have applications that we fed and indexed those PDF documents. For example, I have a UK housing PDF. Well, I'm not going to scan through the entire documents because it might take me 10 minutes to understand what this PDF is and explain to you what it contains. So I just want to quickly test out on my web application. This is an open source link on Hugging Face, so you can remember the URL that you can test it offline when you go home. Let's see, how does my web application understand this PDF? I'm going to ask a question like what city has the highest average housing price in UK? Previously in keyword search application will look for the keyword looking for UK and then match in your document, right? In this multimodal RAG, I assuming it would try to look for the parts in your PDF that it's related to this question and then fed those parts of the PDF and then try to send it to LLM and ask it to generate the answer. So in this demo, it will be able to retrieve the answer based on the information provided on the tables from the file. It will return the answer that the city with the highest average housing price in the UK is London, and the average price is this amount. And then we can also show in this web application that there is a relevant source, and this is a part of the PDF file that if the search find out, and this is a table information that extracted from the information, and you can see it was able to do simple math calculation and find out, oh, actually, London has the highest price of the housing, and it will return you the answer in one sentence. So this is an example of multimodal RAG, how you can fetch your important piece of information from your PDF and generate the answer. And coming back, how do I make this multimodal RAG that I understand not only text, but also image and table? In approach 1, we try to ground multimodalities into text. So the first phrase is, we have a PDF documents that have different components. You try to identify which part of them are tables, which part has text and image. For table, you try to convert them as CSV string, and for text, you try to trunk the large size of the text and then make it into smaller chunks. For image, we try to save them into individual image files such as JPG files. So we have different ways. In our demo that we built up, we use Llama parser. You can also try to use like Amazon text extract. Those are pretty trending. Also, we can try arrange dot parser. Those will help you to extract the components from your PDF files. Later, after we have different components extracted out from based on each modality, we can try to now transform them into textual representation. In this transform phase, we can use ML inference processor. Like we said, when we ingest documents, we can connect to remote model services. In this use case, we use Bedrock Cloud 3 in our demo. Then it will try to convert this graph table and generate image caption. Now we have the capability from the large language model that can generate the text representations from your image. Then you can try to generate text embedding based on the image caption. Again, we can use another ML inference processor, and then in here, you can use a Titan embedding model so that it can convert image text into embeddings. Looking at the documents that are actually stored in OpenSearch, it will have the process image caption, and then along it will have the vectors that are stored on the second field. And we also store the metadata, like this is the image type as a source, and we also store the file that are actually stored in your local cluster so that it's traceable. So this is how we handled an ingest image so that it has image captions and vectors stored in a KNN field. Similarly, for tables, we can do similar processes. Remember earlier, we extract the table into CSV string. We can use the same pipeline that it will leverage the LLMs to generate table summary into textual format. And then we can use the same Titan embedding models to generate embedding and store on the same KNN field type. So later, when we are getting the queries, we can use this KNN field type to retrieve using vector search. So let's walk through the entire multimodal workflow on approach 1. We have the PDF ingested, extracted into different format image, and we have textual formats of image captions in text. We have tables, getting table summaries, and then all of them are storing on the same single document fields. Later, when we have the queries sending from the user, we conducted the vector search, looking up into this document. Then you can tune your queries using filters, and then you will fetch the relevance documents as a bundle context, and those can be sent into LLMs and try to use the LLM intelligence to answer the question. Similarly, in the demo, we were able to show you the answer, and also it can list the references, that what was in the search, and what was the tables, and what their tables text information like this. So this explains the first approach, grounding multimodality into text approach and use vector search. I have been seeing in these last couple of days that many companies are using very similar architectures. It has really good results that because as a company, you have a pretty good precise controls on how you want to handle different modalities. You can control some of the tables and graph processing, like you can apply language translations, you can control how long the textual representation can be. So you can have a lot of precise control. And it's easier to trace and debug in this index because you have all the data processing workflow stored in one single index and use it for vector search. And it also simplifies index mapping. But the approach 1 has been here for some time, and we have been finding some of the issue of this approach 1 is because we have pre-processing layer, we might have some information loss issues that depends on how good you extract the textual formats from your multimodality. You might miss some of the color codings from your tables that is not captured in the textual format. And also this pre-processing layer decided the qualities of how good your data is stored. And you also have to think about invoking multiple LLM calls. If you pick your poison, some of them are pretty expensive if you are calling them multiple times. But if you're using open source and local LLMs, they are free. But you also have to think about the runtimes of multiple models. It depends on the models that you choose. So this is approach 1. And Praveen is going to talk more about approach 2 using a vision language model.
Thanks, Mingshi. So we just covered the approach 1 to handle multimodal PDFs, right? So we are converting all the different modalities into one single modality of text, and then we convert them into embeddings, and then we don't lose the insights from different multimodalities that is existing in your PDF documents. Now let's go into the approach 2, where we're going to rely on vision language models. Okay, so when we hear about vision language models, what comes to our mind, right? So these vision language models have great image understanding capabilities. For example, you just give a piece of an image to Claude 3 Sonnet or ChatGPT. It understands the image thoroughly. It knows each and every corners of that particular image, every part of the image, the patches, and then it will be able to generate a detailed description of that particular image. Or in case if you want a shorter caption, yes, it can generate. This is what we know about VLMs. But since the beginning of the last year, a research paper came out, and the authors were thinking differently. How about using these VLMs not for just generating text based on images, but for information retrieval use cases, which means you can making these VLMs compatible for vector search. That was the idea, that was the research paper that came out, and as a result, multiple models were introduced, which were fine-tuned on powerful VLMs, we have VLMs like Polygemma, we have VLMs like 1.2.5, anything, whatever exists in the market. They took all these powerful VLMs and then they were able to fine-tune them to make them compatible to produce multiple vectors given an image, so that you can use them for information retrieval use case. So we have like 3 models for now which can do this. One is ColPali, the second one is ColQuinn, and third one is GINA4. ColPali and ColQuinn are from the same research paper, from the same authors that came up in the beginning of the last year, and GINA4 is very recent one. Okay, so as I told you, like one of the common things across these VLM-based embedding models is that they use a powerful VLM as their backbone. And in context of these models, a document is nothing but an image of a PDF page. Say like you have 1,000 or millions of PDF pages. What you do is like you take them, loop through your corpus, and take an image of every page and send to these models. And as a result, these models is going to give you multiple vectors for every page, which you then can store into a vector store, and then perform a vector search or a RAG use case. As you see here, when you just give a document page, which is like a one page of a PDF document, the model splits it into multiple patches. Okay, for example, ColPali splits a PDF page into 32 cross 32 as 1024 patches, and then it's gonna give one vector for each of the patches. Here is where every patch is considered as a separate image. Okay, and once it generates a vector for every patch, then comes the important layer of the large language model, where all these patch vectors get into a text-based large language model, and they get contextualized. Here is where an important step happens, because think about a PDF page. And for example, in the first part of the PDF page, you have a figure. And say in the last paragraph of the same PDF page, there is a reference to that particular image which is present at the top. So now, in this second step, where it gets passed to the large language model, the patch vectors present in the part where the figure was present, those patch vectors get so closer and similar to the patch vectors present in the last paragraph of that particular page. Here is where all the broken puzzles get together to form a meaning. Finally, what you get is you get 128 dimensional n vectors for every PDF page. Likewise, on the query side, you pass your text query, and you're gonna get one vector for every token. So now we have multiple vectors on the document side and multiple vectors on the query side, and then comes the scoring mechanism. So this scoring is quite different from how the usual scoring between two single vector happens. Okay, usually we have one document vector and one query vector, and either the scoring happens by cosine similarity or Euclidean distance. But here, the scoring is going to be different because we have multiple vectors on each side. So that's where this scoring mechanism is called as late interaction mechanism. This means all the query token vectors interact with every document patch vector. Okay, so that everything interact. And the name late interaction came from the fact that all these vectors interact only on the query side, only on the scoring side at the last layer, but not on the beginning layer. So that's why it's called as late interaction model. And on the mathematical terms, this score calculation is called maximum scoring, maximum similarity scoring, which means every query token vector is compared against every document patch vector. You get to know the maximum scoring patch. Likewise, you're gonna get a list of maximum scoring patches for every token vector, and finally you add them. So here is where you get a good interacting query token vectors and query and document patch vectors, and the score is on top of that. Okay, so how do we use such VLM-based embedding models for search? Here, the problem statement is going to be given a query, find the top n pages that has relevant information for the query. Okay, so say you indexed 1 million pages, you just want to know what are the top 10 pages that has relevant information for my question. So on the offline indexing side, you take all your documents, and then you send it to these VLM-based embedding models. You get n vectors per page, and then you index it into OpenSearch. And then on the query side, again for your query, you get multiple vectors for your based upon your number of tokens. And then now you do a KNN search, and as a result, you're gonna get top n vectors, which are top n documents, which are nothing but top n pages, which is sitting in your OpenSearch. Okay, so now we got the top n pages. Say we got top 100 pages, and now we're gonna do a maximum similarity re-ranking, that is the token-to-token interaction, and then calculate which top documents can be rescored again. So the top 100 pages again go through this maximum similarity re-ranking. Again, it gets reordered, and finally you're gonna get the optimal top n or 10 pages that's going to have relevant information for your query. But that's not all, right? So we got the top pages, but how about answering the exact question? Say for that question, for example, I have a question called what is the quarterly relative return? To answer that exactly, what you do is you take the top n pages that was obtained from the retrieval and re-ranking, and then you send it to a vision language model and give a prompt something like, okay, this is my question, and these are the top 10 pages that I have, which is having answer for this particular question. Okay, so now this vision language model will be able to answer that question. For this, you can use anything like Nova, or you can use ChatGPT or Claude 3 Sonnet, anything. It's about we first find the top n pages and send that to a vision language model to get the final answer. Okay, so what are the best practices to implement a multi-vector retrieval with OpenSearch? First thing is, since you're gonna have multiple vectors both on the document and the query side, you need to reduce the number of vectors, because multiple vectors per document is going to increase your storage and memory requirements. So you can do mean and max pooling or clustering pooling to reduce the number of vectors per document. And on the query side, you can also, since queries tend to be shorter, you can just reduce them into one single query vector. And even the authors of that ColPali paper, from their experimentation, they found that the pool factor of 3, you don't lose quality. The quality was maintained with 99.7% of the original quality. So we are good there. And on top of that, you can also apply quantization techniques with OpenSearch up to 32x compression OpenSearch provides, and also you can leverage disk ANN of OpenSearch to reduce the memory requirements. And for storing these vectors, you can leverage the nested vector field of OpenSearch. And on the query side, you can use nested vector query. I will just show you how that looks on the mapping side. Okay, so just to show you a sample document. So this is we have already indexed 7,000 plus pages into this index, PDF pages. And as you can see here, the page subvectors is my nested vector field. And inside that, I have lot of subvectors. Every vector is 128 dimensional, and this is like one single document, which is nothing but a page of a PDF. And also I store where is that PDF page, and also I tell what is the page number. I store everything into OpenSearch. Okay, let's quickly get into a query to see how this works basically. Okay, as you can see, I have asked a question, proportion of female new hires in 2021 to 2023. I mean, this answer is somewhere sitting among the 7,000 PDF pages. It was able to answer it using this ColPali approach. And as you can see here, I got this as the source. I got this PDF page as a source, and you can see here, this chart is having the relevant information for the question regarding the female new hires in 2021 to 2023. And that's not all. Since we have multiple vectors for tokens and for documents, you get to know why a document has got a particular score. which is not usually happening in vector search, right? Because vector search is more like a black box. You don't know why a particular document is scored so. But with this multi-vector relate interaction models, what you can do is you get to know like which token of my query is actually contributing more to the score. So that's where you can, for every token, you get to know what was the scoring that was happening. For example, the important word here in the query is female. Let's just zoom into the female query. And as you can see here, all the boxes in the PDF page is nothing but the patch vectors, okay? And where it is more highlighted, which means the female token is like similar to those patches in that PDF page, which is this area, this highlighted area, and you can see that's where the word woman is there, okay? So that's where you get to know why female has got 0.62 score, because it is contributing to that area of the PDF page. So you are making vector search explainable now. Okay, so finally, how to make the right choice? Yeah, it depends on your requirements. First, if you have if you have a smaller corpus and your documents are text heavy, then go with the approach 1. And also, if you want to do full text search on top of your data, not just RAG, then approach 1 makes much sense. And if you have complex PDFs where you have a lot of multimodal elements, and in order to avoid the pre-processing cost of parser cost, you can go with the approach 2, which is like based upon this VLM models. And this space is quite innovating faster as we are seeing more models are getting introduced. So I think already there are vector engines that supports this multi-vector relate interaction models, and OpenSearch has been added to the list. The only thing is like OpenSearch does not now have the native support. We have to use a scoring function inside OpenSearch, but we also have raised our RFC. The first QR code is RFC, which is a native support for late interaction models in OpenSearch, and the second one is the OpenSearch AI demos, the demo platform that you saw. That's totally open sourced. Explore and play along with it. And the third one is the ColPali OpenSearch tutorial. That is a complete notebook that you could just run in your notebook instance so that you can see how ColPali works with the sample data set we have given there. And finally, the latest addition from Mingshi is having a dedicated ML connector for ColPali model. So you don't have to do the machine learning inference for ColPali model on the client side. You can just create a connector inside OpenSearch, and OpenSearch can contact to the SageMaker model, which is ColPali, and then generate vectors automatically for ingestion and search. So making your application lightweight. Yeah, so that's it we have. Any questions, and also feel free to take a photo of your QR codes.
Questions?
Yeah.
I have a question on the second approach.
Yep.
Today's AI models have very long context windows, like up to 1 million tokens. Instead of chunking up a PDF into smaller chunks, why not create an embedding from a PDF and then say dump 10 different PDFs, the entire PDF that's relevant to the question, and to the AI model itself?
Yes. But how do you find say you have million PDF pages, but how do you find which are the pages that might be more relevant to my question?
So typically with companies, you don't have a 1 million page document. Mm-hmm. You have, say, 1 million PDFs that are each 10 pages or 15 pages.
Yeah.
So if I just create the embeddings on each PDF, and because the context windows are getting larger and larger, then when a prompt comes in, you just pick the top 2 or 3 PDFs in their entirety and dump it into the context window. Like, how does that compare? Because then I do less work, right? How does that compare to the second approach?
So in OpenSearch, like you mentioned, because this approach is more for like handling different components within one PDF, you want to narrow down to the specific tables to answer your question, then approach 1 or 2 would be more ideal. But if you just want to generate embedding for each of the page, and you just want to find out which page that is relevant to your questions, then you can use image embedding. Like many right now that we have image embedding model, for example, like Titan Image V3, you can generate for each page of the PDF generate one embedding token for each. But that is also durable for if, for example, that it would be more ideal if you have a PDF, this one image that is standardized, like this, the entire one is for text, the second one is entirely for images. That will also work. But if each of the PDF file has rich media, they have mix of image, table, and text, that search relevancy has to be lower because you actually compress the entire image into one embeddings. The search relevancy will be impacted. So you have to think about the trade-off. If you want to have more relevancy, search relevancy to your query token, and you want to understand each part of your images, you can try to use those more advanced ColPali model, or you can try approach one that you want to extract them into single components. But if you want to use just one single token that runs faster, but you might sacrifice some of the search relevancy.
Maybe I couldn't formulate my question correctly. Actually, I was thinking I have, say, 1 million PDFs, 10 pages each, and I create an embedding on each PDF.
Okay.
And when the prompt comes in, I retrieve the 3 PDF documents, 10 pages each, and I just dump them into the context window for the LLM. Right? Because what's different today than, say, 6 months ago is these, like they can process, all of them can process PDFs natively, and they have very large context windows. So I don't have to do any of the processing, except just creating an embedding vector for each PDF.
Yeah, that's
When you say each PDF, you want to generate
one
vector
embedding.
for the
Just one, like one vector, like that represents that PDF.
Yeah,
Okay.
that's I've seen some of the applications do that, but that actually will cause some of the problems. So when you talk about many of the context engineering right now, you want to send us very more accurate pieces of your documents that related to your query. For example, you want to send, you actually get top end results from your PDF. Actually, maybe just 2 sentences is related to your query. The rest of the 90% in that PDF might be not relevant to your question. Then, but you send the entire page of the PDF to LLM, then this might misguide the answers when LLM get the context.
Maybe if you can jump offline for even more
Yeah, we
details,
can talk about this offline.
Any other questions?
I have another question.
Go ahead. If nobody has anyone else, I can go. Okay.
Yeah, maybe you can go with the second question. Then.
Approach number 1 and number 2, which one do you like? Are customers using, like, or the people?
Now more on the approach 1.
Now more approach.
Yeah, because like these models evolved so recently, like I would say beginning of the last year, and so maybe like now just not all vector engines support late interaction models. There are some storage and memory constraint, more storage and memory requirements for these models. So yes, it's not been into production for customers as far as I know.